Hello all, welcome to the next lecture of the course. In this lecture, we shall see how to do CFD analysis for a two-stage axial turbine case. Here, there are 4 blade rows, HP NGV, HP turbine, LP NGV and LP turbine. Let us see the specification. This is the RPM of HP turbine and LP turbine. They are in different spools, so the RPMs are different. The total pressure at the inlet of HP NGV is 1200 kPa and the total temperature is 1400 Kelvin. The static pressure condition at the exit of LP turbine is 150 kPa. The number of blades of HP and LP turbine and NGV blades are given here. The broad specification of the turbine is given here. The mass flow rate is 79 kg per second. The total expansion ratio is 5.12. The total efficiency is close to 89%. This is the workflow for this turbine case. The mesh is already available for all 4 blades. We will import the mesh in CFX preprocessor and then set up the case and do the post-processing. The things which we will learn in this particular chapter are how to do analysis for multi-spool turbines in CFX, specify material property at high temperature condition, initialization in preprocessor and solver, and the post-processing turbine stages for multi-stage compressors. Now let us open Ansys CFX. Let us open CFX preprocessor in standalone mode. Now click New Case, choose Turbo Machinery, and click OK. We can uncheck this information, click OK. The machine type is Axial turbine. The axis of rotation is X-axis. Click Next. Right click and add component. The first stage will be stationary, that is HP NGV. Click OK. We shall browse the file. We shall import the mesh file HP NGV. Click Open. Now we shall import the other components. Now all the 4 components are imported. We can see the HP turbine as well as LP turbine here. We shall specify the RPM for LP and HP separately. For HP it is 9970. For LP it is 9630. We can see the arrow pointing at right direction for both high pressure turbine as well as low pressure turbine. So we shall proceed forward. Click Next. We can specify the boundary conditions here. Let the reference pressure be 0 atmosphere. We shall specify total inlet and static outlet condition. The inlet total pressure is 1200 kPa and the temperature is 1400 Kelvin. The static pressure at the exit is 150 kPa. We can click Next. By default, CFX has taken all the interfaces and boundaries. We shall not check now. Now we have to specify the material property for high temperature application. Here we can scroll down and then we can see the materials. By default, we will be giving air ideal gas for other compressor cases. But for turbine case, we have to specify the air properties at high temperature condition. If you see, the temperature at the inlet and outlet are given here. Similarly, the pressure at the inlet and outlet are given here. So we can take average temperature based on the inlet and outlet temperatures. Similarly, we can take the pressure as an average. So for this elevated temperature, that is 1162 Kelvin and 750 kPa pressure, we shall find out what is the CP, that is specific heat at constant pressure. So there are several calculators available. We can find out the specific heat of air using the data available online. We can check from engineering toolbox. Here we can see the variation of heat capacity at constant pressure as well as constant volume with respect to different temperature as well as pressure. In our case, we can take the pressure as 10 bar approximately and the temperature as 1100 Kelvin. There are calculators available to find out the value of CP. So the temperature is 1162. The unit is Kelvin. Similarly, the pressure we can choose roughly around 10 bar. We can click calculate isobaric specific heat CP. So we can find out that the specific heat is roughly 1166 kilojoules per kg per Kelvin. We shall take this specific heat 1166. So the CP value is 1166 joules per kg per Kelvin. We can find out CV from CP and R. CP is equal to CP minus R, that is 287 joules per kg per Kelvin. CP is the specific heat at constant pressure and CV is the specific heat at constant volume. We can find out the specific heat ratio based on CP and CV. Gamma is given by CP by CV, that is 1.327. Based on this gamma, we can find out gamma minus 1 by gamma. This term comes in efficiency expression. Gamma minus 1 by gamma is 0.2461. We shall feed this input into efficiency calculation. Also, the efficiency of turbine is given by this formula. Actual work done by the turbine divided by the isentropic work which can be done by the turbine. Here the efficiency formula is finally converted to this format. 1 minus 1 by temperature ratio divided by 1 minus 1 by pressure ratio power gamma minus 1 by gamma. We shall go back to CFX and specify this expression for efficiency calculation. Next we shall update the material properties. Scroll down to materials. By default we have chosen air ideal gas. Now we shall modify this. Right click and duplicate this material property. We can rename this. Here we shall specify the property of air at high temperature. Go to material properties. We shall change the specific heat to 1166. This is one level of accuracy. Here we are specifying the flow properties of air at high temperature. If you want next level of accuracy, we have to go to basic settings and then change the materials group to only air data. We have to remove this calorically perfect ideal gases. If we choose calorically perfect ideal gases, we will be specifying one CP value for the operating temperature. Now, since the operating temperature will be varying from inlet to outlet, we can give the CP value as a function of temperature. For that purpose, we have to uncheck this calorically perfect ideal gas and choose only air data. Now, come to material properties. Here you can specify the CP value as a function of temperature. Here you have to specify the CP value as an expression for which you have to enter the coefficients of those equations. As of now, we will stick to calorically perfect gas and then specify the CP value for higher temperature condition. Now the CP is 1166. Click OK. We shall double click each and every domain and then we can change the materials to combustion gas. Now we have successfully changed the material property. We shall provide the expressions next. Insert mass flow in functions mass flow physical locators 2D S1 inlet star 46. There are 46 HP NGV blade. Similarly, for mass flow outlet, we have to specify LP turbine blades. R2 outlet star minus 85. There are 85 LP turbine blades. Now we shall create expression for expansion ratio and efficiency. The efficiency formula is given by 1 minus 1 by temperature ratio divided by 1 minus 1 by expansion ratio power gamma minus 1 by gamma, which is 0.2461. Now click apply. Now we can monitor these parameters in output control in Solver Manager. We can also provide global initialization for this whole domain. For that, we have to right click flow analysis, go to insert and specify global initialization. If you know the velocity, static pressure and temperature conditions for this domain, we can specify that so that we can quickly converge the results and then get the final solution. This is one way of initializing the domain. The other way is to initialize in Solver Manager. Now we shall run the case with the first order condition and then we will save that result file as an initial file. So in the next step, we can generate the case with a higher resolution and then we can give that first order result file as the initial condition. Let me show how to create the first order case. Go to Solver Control, change the advection scheme to upwind, turbulence numerics to first order. We can keep the maximum iterations as 100 and we shall keep the residual target as 10 power minus 4. Click OK. We can save the case file. We can save it as turbine initial case. Save the definition file. Go to Solver Manager. We shall first solve this initial case. Start run. So once this initial case is done, we can use that as an initial file for the next case. Let it solve. Here we can see the initial case converged. Now we shall go back to preprocessor, change the solver control to higher resolution and second order, specify higher number of iterations, increase the residual target, click OK and save the case as turbine. This is the final case. Click save. Now open Solver Manager, go to new case. Instead of the initial definition file, we shall choose the final definition file turbine.def. Click open. You can go to initial value settings, start initial values, and then choose the initial file which has been generated. Click open and then start the run in parallel mode. Click start run. Here we can see the converged solution for the high resolution case. Now we shall post process this result. By this way, if you have any issue in solver convergence for the initial design, you can specify first order and upwind scheme to quickly get a solution which you can use it later for the next second order case. Let us open CFD post, go to turbo mode, initialize all components, calculate velocity components. Now let us load the turbine report template. Scroll down to report, right click report and choose report templates. Here you can scroll down and then find turbine report. Click load. Now it will load the report templates for turbine application. Now the report template is loaded. We shall go to report viewer. Here we can see all the reports of the turbine case. We can see the total mass flow rate, pressure ratio, temperature ratio and total efficiency and all other parameters. All the important plots and charts are generated here. We can publish this to view it in PDF or HTML format. Okay, thanks for watching this video. I will see you in the next lecture.